Okay. Alrighty, I've turned it on.
Okay, thank you, Jacob, and thank you, everybody, and thank you for our interns that are joining for the second edition for the Agarwal Open Source Festival final presentation. Today we have three fantastic presentations coming from Sharad, and then Milind and Harish. And like yesterday, Jack will be our master of ceremony. So without any delays, let's kick it off. Jack?
Yeah, sounds good. Thank you. So first up, we have Sharad with the project Pushing the Limits of VW with Flatbuffers. He was working with Rajan for the project. So when you're ready, Sharad, go ahead.
I'm just going to share my screen. Can you tell me when you see my screen? Yep. All right. Okay. Hello, everyone. My name is Sharad, and I've been working over the past summer with Rajan and Olga over the later half over integrating Flatbuffers for VW to push its limits in terms of speed and performance. And this is a small presentation of what we have been up to till now. So a little bit about myself before getting into the presentation. I'm a senior year undergraduate student at BITS Pilani, India, majoring in electronics, but interested in machine learning research. Do not quite have the knowledge to exploit it yet. Currently pursuing my bachelor's thesis on safe reinforcement learning. Have a bit of work experience in reinforcement learning, robotics, and efficient deployment on nano drones and edge devices. And I've also worked on large-scale machine learning for data that comes out of the Large Hadron Collider at CERN. So getting back to the project, a little bit about VW before talking about Flatbuffers and how we integrated it. It was first released in 2007. It's known because of its ability in being really fast and flexible in integrating new algorithms. Majorly deals with online machine learning and has a really good amount, a really great deal of software optimization techniques through hashing, great features like all reduce reductions, etc. So the current landscape of how VW does its job is essentially through two major components, probably the most simplistic view. We have a parser and a learner, and the parser will essentially go through each and every line, read everything, then convert all the floats, and create examples, and then pass it to the learner, which would do its job on another thread and print out the results. So what can we do better over here? One of the main issues is that the same copies of feature groups or namespaces could be read again and again if the data sets are really big. So there's also an extra parsing step with respect to the float values that we have, since we need to convert them. And it turns out that this is one of the costliest operations that happens during the whole parsing step. So, and also we sort of lack like a schema or structure for the input examples that we have currently. So in terms of the formats that we have, so JSON, DSJSON, they're sort of slow. They don't really have a schema structure and allow for flexibility. Text is fast because VW's parser is really optimized towards it. There's no schema structure. There's not a lot of flexibility as well. Cache is really fast. It has no structure, no flexibility, and there's no user interface for creation as well, which is a big problem. But Flatbuffers, it's really fast. It has a structure through a schema that we can build, and it has a lot of flexibility as well. And finally, we can also have a user interface for creation of Flatbuffer, like data sets or input examples. So, so just going over the advantages of flat buffers again, there's zero copy deserialization. The float values are never really converted. They're just directly allocated from the flat buffer to directly the examples. There's a lot of flexibility through tables because we can have optional fields in tables. Everything is strongly typed, even the schema itself. So all the compiler optimizations are taken care of while parsing. There's a lot of reuse of data in the buffer. So if there are a lot of feature groups that are same in different examples, then we don't really need to store them again in the second example. It could just be the offset from the first example. And finally, there's cross-platform and multiple languages support. So it goes well with VW. So going over the goals, we want to develop a flat buffer schema for input examples. We want to develop a utility to convert data from existing data formats to flat buffers seamlessly. And finally, once we have this flat buffer, we want to inspect this flat buffer. So going over the first one, which is the schema, this is what it looks like. And we have the outermost one, which is an example collection, a table. It has, of course, multiple examples, each example having multiple namespaces and one label, and each namespace having multiple feature groups. And the label over here is marked in red because our label is a union. So we can have multiple different types of labels, all the different types of labels that VW supports at the moment, which are 9 of them. And the advantage over here is, of course, that since it's a union, only once it's filled, it's only one of these. The space occupied is from only one of these. So I'm going to do a short demo of how things work. So here we have a data file, simple.vw. And let's see the first line, which is there's a label, which is one namespace, and there are a lot of features over here. And to check, let's just check how many lines there are. So we have about 100,000 examples in this file. So first we need to convert this. So we can do build util flat buffer to flat buff. So over here, the command line arguments remain the same. And everything would be populated in the example struct just how VW works normally, but except for passing the data to the learner, what would happen is it would just sort of populate the flat buffer. So so the advantages over here is that using VW, we don't really have to specify a flag for what the label is. So it's just populating the data and then populating the flat buffer. So we have our flat buffer, which is created. We can check the sizes. So we have simple.fb, which is 151 megabytes, simple.vw, which is 135 megabytes, almost the same. Now, to run this through VW, we can just do VW -d-data simple.fb. Just to avoid any caches, we have cache cake. So it runs through VW really easily. And just to check if we have the correct output, we can go over the original file that we had. So so we can see that the average loss over here is something 417, 637, just to see if, just as a sanity check, the 637, 417, everything remains the same. Not sure if you noticed, but flat buffers is, of course, much faster over here. OK, so that was for the demo. And all right, so what's essentially happening is flat buffer, the parser would essentially get features from the flat buffer and directly allocate them to the example struct rather than doing any sort of conversion, which happens in text. And this essentially leads to a lot of speed or performance optimization. So a little bit of performance comparison. So we have a label type, text parsing time, flat buffer parsing time, and how much times it's faster. So we have our simple label, which is 0.8 seconds. Flat buffer is 0.48. It's about 65% faster. Contextual bandit is about 1.31 seconds for the text and 1 second for flat buffer. It's about 30% faster. So one thing to note over here is that there's a difference over here because the data files are sort of different over here. The contextual bandit file does not have a lot of floats. So the more number of floats that we have in our file, and the bigger and the more bigger floats there are, the text one would essentially take more longer to convert them and parse them. But for flat buffer, it's direct allocation. So given the same sort of features, there should not be a lot of difference between different label types. Over here, the difference is because contextual bandit data sets often have just words rather than floats. So just going over some of my learnings over the summer, Bhopal Rabbit itself. I've been exploring machine learning research and performance optimization because of my efficient deployment work. It's great to see and learn something that does things so well as other frameworks do not. Of course, flat buffers itself, I had very, very little experience with flat buffers before, but it seems like now I know how to build things with flat buffers. C++, good practices, techniques. Very thankful to Rajan and Olga over spending hours and days with me during the whole summer. A little bit of gRPC with flat buffers on the side, which I did for one of my other projects. The concept behind reduction stacks, because I never really saw them exist in an industrial product before. And of course,
5 minutes left. Just letting you know.
Yeah. And of course, contextual bandits themselves. So future work could be a little bit more schema optimization for for example, use of structs, etc. More optimized creation of flat buffers. At the moment, flat buffers that exist right now, the way they're created, they do not reuse the data or feature groups that exist. So if that could be done, then the speed ups would be a lot more as compared to right now. And flat buffers for model checkpoints that would lead and speed up when we're loading a pre-trained model or something. And maybe parallelized flat buffer parsing with having a prefixed size appended before every example in the flat buffer. So sort of like combining the two reinforcement learning, two of the reinforcement learning open source projects that we have. Okay, yeah, that's about it from my side. Thank you so much. Were there any questions?
So I had a question about the size of the flat buffer. It's a little bit surprising to me that it's as large as the text size. And I remember we were discussing this previously. We thought about maybe trying to compress the flat buffer. Have you played around with compressed flat buffer? Yeah,
so we actually, so right now the flat buffer size is greater because there's not a lot of reuse in data. So the schema that looks like right now, it's sort of really nested. So it's avoiding a lot of the reuse in data that can be done. So once that's once we can get rid of that, there's a lot of reuse, and it could potentially lead to smaller files. So Olga actually performed some experiments and over this, and it sort of led to like a really good sort of speed up. So over here, for example, we have the cache IO buffer, which is taking some 144 or something, and the flat buffer prehash, which is 116. And if we go about the sizes, then I have the sizes, which I can show you for the, yeah, just a second. So over here, yeah. So this is like one of the initial experiments where the flat buffer is actually smaller than the original file. So running this through VW could potentially make it all much more faster in general.
So if you gzip the symbol.fb, how big is it?
I could try that.
Yeah, I think Olga did some experiments with this. I mean, unfortunately, she isn't here today, but we lose all the performance of flat buffers. It is similar to like gzipped performance of text. But if you do the shared examples, there's a pretty dramatic reduction in size and a much greater, improvement in performance. So gzip, you kind of lose the performance because you basically have to touch all the memory anyway if you're doing gzip.
You can read gzip on a stream.
You can, but essentially you kind of lose all the benefits of flat buffers, which basically doesn't have to go through each byte in memory to do its work. So it just does like a mem copy with like, and then it just has to do all the bytes of memory. Like they don't have to go to the CPU. Whereas with gzip, you kind of have to do read the stream, which means every byte has to go through the CPU, and then you have to then push all of that back into memory. So basically, you kind of lose the real advantages of flat buffer. So what we found was really like there is it basically, I mean, I don't know the exact numbers, but it basically it doubles the time taken to run. And the compression is about the same as if we actually shared the examples. So instead of like running gzip, if you just said, okay, I know that these 10 examples are the same, or whatever, you get like fairly large increase in performance and a nice reduction in file size. But Olga has those numbers, so unfortunately we don't have them here. But
Okay.
Might be good to ask her. I think there was another question. Jacob might have had another question.
Yeah, I was wondering what the relative sizes of the bits of data in the flat buffer were that were taking up this extra space over the cache format, because my guess is this is mostly due to a little bit of overhead from flat buffers itself, plus the fact that we're keeping the original strings around.
Yeah, I think.
So then the question becomes, what if instead we had all the strings concatenated into one giant buffer, right? Or some sections of buffer that could then be decoded, but only if they're needed.
Yeah, I think
right, and then you can outright skip them if you, and those can be gzipped, right, in pages.
Yeah, so we didn't get a chance to do a lot of that kind of work. This took up pretty much everything we had. So I think there is some scope there for further optimization. But I think like the big win really is sharing examples. That's like a dramatic difference.
Right. I'm just worried about the online computational cost of figuring out which ones are shared and which ones are not.
Yeah, that's true. Yeah, there is some cost there. Now, if you could expose it to users who do know when they're sharing examples, maybe there's something that can be achieved. That would, the cost then is like you don't have to do your own comparison. So
no, if it's a user control system, it becomes simpler.
Yeah. So the thing is, you don't actually have to change any code in VW to take advantage of that. Meaning, as long as you create a flat buffer file with shared examples, VW does not know the difference. So there won't be any code change. It's just how you create the example file that's different.
Makes sense.
So,
all right, I don't want to keep randomizing us,
so
I'll follow up offline.
Yep.
Do we have any other questions? Cool. Thank you, Sharad.
No problem. Thank you.
Yeah, thank you. So let's move on to Milind, who is working on Contextual Bandit visualization in Jupyter Notebooks. He was working, I believe, with Marco.
Yes. Paul in the beginning of the summer and then Marco. Yes.
Yeah, cool.
Let me start sharing my screen. So you should be able to see the first slide with the title right now.
Yep.
Awesome. So, well, thank you everyone for taking time to come attend these presentations today. As you can see, the title, and as Jack mentioned, is Contextual Bandit Data Visualization with Jupyter Notebooks. And that's what I'll be running through today. Before I go into the details of the project, let me just introduce myself real quick. My name is Milind Agarwal. I am a final year class of 2021, bachelor's and master's student studying computer science at Johns Hopkins in Baltimore. This summer, I was lucky to be mentored by not one, but two investigators at MSR, Paul for the first half of the summer, followed by Marco for the second half. So let me start by motivating the project a little bit and talking about why this call for proposals was sort of sent out. Why do we need visualizations for contextual bandits? Well, visualizing your data is always a good first step to jumpstart your analysis. And using visualizations throughout your analysis at various checkpoints also allows you to pause and reflect and visually probe your policies to gain a little bit more insight into how your analysis is going. Visualizations also have a major benefit of being very intuitive and easily digestible to understand your data, your policies, your actions, and your results, and also to convey them to customers. So that brings me to the next slide is, before you start implementing anything, it's always helpful to identify your customer base, your user base, and what their needs are so you can tailor your approach or your implementation to that. So who may want to use this library? Well, having presentable graphics that would allow you to explain your analysis in an easy to understand way would be very helpful for customers. For independent researchers out of MSR, it is helpful to have visualizations so that they can better acquaint themselves with the functions and the algorithms built into VW for contextual bandits, and even customize the code base that we provide to suit their needs and their use cases. And last but not least, using visualizations that work with different VW formats can also be very helpful for in-house research at MSR, because our investigators use do a lot of diverse kinds of analysis with different kinds of data. So having a library that works with different formats would also be very helpful. So by identifying our users, what we end up doing is also highlighting the needs and the considerations that we should keep in mind. So this provides us with high-level considerations. It's important to have clean visualizations that are not too complex to understand. They should be customizable, because we have people not only working with standard data sets as MSR investigators do, but also in various domains in RL research. It should be easy to use and robust, so it should work with different kinds of data. So now that we have our high-level guidelines, let's step back and go back to the call for proposals that Marco put out for this project sometime in the spring. So here are the verbatim goals from the call. It mentions visualizations for feature importance, action distributions, action or reward distributions conditioned on a feature or a model used, and benefit and comparing different models. So this summer, we ended up redefining and refining these goals to make sure that we could work on them in order. So we ended up putting them into different bins that I'll go over with you today one by one. So we split them into one exploratory or pre-training phase. Then you could have visualizations during your policy training process, moving on into analyzing that trained policy and understanding feature importances. And then even further to understand how your policy is interacting with your actions. So just note that today when I go into the following slides, I'll be showing a highlight graphic for each section instead of going through each and every visualization you could produce with every function, just so we are respectful of time. So for the exploratory section, you can visualize feature correlations, hierarchical relationships between features, and use this to prune your data set. So on this particular slide, you have a graphic, which is a tree-based diagram that's illustrating hierarchical correlations between features in this OpenML dataset with 54 features on the x-axis. And on the y-axis is word linkage distance. You don't really need to understand the specifics, but it is a distance-based metric, so it's positive and it starts at 0. And what this means is the smaller, so the closer to the x-axis the value is, the more strongly correlated these two feature vectors are. So the smaller the distance between them, the more correlated they are. And what this kind of visualization conveys to us is correlations across all features and how and it organizes them based on their strength to help us understand a more hierarchical structure in your entire feature collection. This is very useful because you can identify clusters of closely related features and even use this to prune your data set before you start training, which I'll give you a quick example of. So from the same plot, you can use some supplementary functions in the library to select a threshold. And what this function will do is it will cluster or bin anything that falls below that threshold. So for this example, this is slightly over exaggerated. You probably don't want to fine tune your data set so much, but it really conveys the message. So for a threshold of 2.2, for example, for this plot, you would end up binning your data into 9, right? Yes, you would end up billing them into 9 different bins. And feature 2, for example, the new feature 2 would end up having combined information from everything in red. So all 6 features would basically collapse into one bin. And this way you end up pruning your data set to remove either highly correlated features or redundant features. And a major benefit of doing this through this visualization process is so your policy can learn faster if you reduce your data set size. Awesome. So I'm gonna move on to the next section of our refined workflow, which is policy training. So once you have understood correlations between your features, their structure, and potentially even pruned your data set, you will start training your policies with different parameters. While you're training, you may want to visualize your average reward across your training iterations and use that to compare different policies if you're doing parameter sweeps, for example. So here is an example visualization that you can produce with this library to look at average reward during training for this policy. So it is useful not only, so this kind of visualization is useful not only to visualize the variation in a policy's learning as it continues to see more and more examples. Highlighted here on the x-axis is the iteration count, and I turned on log scale so it's easier to visualize since there's a lot of examples in this data set. And on the y-axis, you'll see average reward. So it's helpful not only to visualize the variation that in this policy's learning as it sees more and more examples with different actions, but it may also help you to gauge a particular data set size where your policy with the parameters you chose is flatlining or stops learning new information, which may help you further tune your parameters. Awesome. So in the next section, we'll move on to talk about another class of visualizations you can produce, which would fall under feature importance. So once you have a trained policy that you've chosen after doing your hyperparameter sweeps, you may want to inspect that trained instance a little bit more and look at feature importances or features that that trained policy is relying on. So here on the x-axis, this is the same OpenML data set that we have sort of modified into a contextual. We're using this supervised data set in a contextual banded way to train this policy. And the feature importance algorithm on this slide is leveraging that supervised data set information. So in this example, you'll see on the y-axis weight or importance that is being computed by an algorithm called permutation-based. It's a permutation-based approach, so it focuses on shuffling a feature and then measuring, based on that introduction of noise into that feature, how did prediction differ with your trained policy, and that will help you understand how much that trained policy is was relying on that feature, as you'll observe when you do this method on a validation data set. There is still work to be done to get DS-JSON support for feature importance. Like I mentioned before, this particular chart displays the same OpenML dataset that we modified to follow contextual bandit formats to train and then leverage that information to calculate these importances. Okay. So I'm going to go a little bit into how that permutation-based algorithm actually works, since
You have
not
about 5
everyone-
minutes left.
Yes, thank you. Might not be exposed to it. So what this is essentially doing is it'll shuffle a particular feature and we'll check how much the policy predictions are affected. There's a caveat to this, which is multicollinearity. So by shuffling one feature, the policy may rely on another correlated feature. For this example, let's say 2 and 4 are correlated. And in the end, you may end up labeling both of these features as unimportant while they might actually be. So it is important. You may not encounter this problem at all if you looked at your data set in the beginning and understand the relationships between your features and their correlations and the structure between them before you start jumping into analysis. But this is something to keep in mind when you're using these methods. So the last section is action distributions. So in this graphic, we're looking at another data set that has 3 actions, and on the x-axis is timestamp, or a proxy for iterations or number of examples, and will help you visualize how your policy is learning or learned while you were training. So the red in the beginning here is, I'm just going to go over the key. The red in the beginning represents uninstantiated policies. The blue sort of horizontal lines that you'll see all over indicate that an action was available in the action set, and this might be different depending on your data set. But for this one, all 3 actions were available from the beginning till the end. And the colored squares indicate different values of reward. Since I'm not really showing the Jupyter notebook today, for coherence's sake, I have a zoomed in slide of what this would look like. If you further zoom in, and you will see more detail. The blue circles represent instances of reward, that a reward was received, yes or no. And the orange at the bottom that you'll see here represents that baseline action, so the first action in the multi-set of your example. So that was a quick overview of an example workflow and some illustrative visualizations from each of our sections of our refined goals and workflow. If you're interested, I am happy to share the Jupyter notebook that we created and I even presented in the earlier presentations. So you can look at the exact function calls and how easy it is to use these visualizations and even customize them to work for your particular data set. In the future, it would be helpful, like I mentioned, that there's some work to be done for more robust support for the DS-JSON format in particular. And I think that would be very helpful to make this even more usable for everyone. I also want to talk about what I've learned this summer through this open source project. First and foremost, exposure to RL. I have had the chance to work with a lot of projects with machine learning, so mostly focused on computational biology or machine translation and NLP. But this was my first exposure to RL, and I'm sure a lot of people here may agree, since you're seasoned professionals in RL. It does get a little bit of time to get used to RL if you're coming from a standard ML background. But I'm glad to have been exposed to this so early in my academic career as an undergrad, and I hope I get the chance to work on more RL problems more in depth. Secondly, I've only worked in academic settings with professors across all my projects, and this was the first time I got a chance to work with an industry lab. The only difference, I guess, this time was that everything was remote, but I was very happy to get the chance to have mentors who were industrial researchers and have the chance to work on an open source problem. I also want to thank Microsoft Research for organizing this open source fest, which thankfully was remote this summer. I think everyone is very happy about that. I want to thank both Paul and Marco for mentoring and bearing with me all summer. I also want to thank Jack for coordinating. I think that's a really important job to make sure we're all on the same page and that everything runs very smoothly. So thank you. And that is all I have for my presentation today. I think I did well on time.
Yeah, perfect.
Yeah.
Thank you, Milind. Do we have any questions?
I don't have any questions, but it looks cool.
Yeah, I'm excited to see this as part of the kind of toolbox we have available for working with Python and RL datasets and that kind of thing. I think it would be really helpful.
Yeah, I think a lot of our collaborators within Microsoft will be excited to use Milind's Jupyter notebook.
100%.
Yeah, very cool work.
I do have a question.
Yes.
Is there a way to like think about the multi-collinearity problem without having to do analysis to figure out, what two features are related? Like, is there a way to do a different kind of? Yeah.
No, I understand your question. It's, I guess you would need to explore a non-shuffling or non-noise based importance method. So we would need to investigate a different class of sort of algorithms to investigate feature importance that would work well with more standard OpenML rectangular data sets, but also with our DSJSON or even Flatbuffer formatting later on. But with permutation importance, it is a caveat that sort of introduces itself once you're shuffling, because there is a reliance that is in features. But I understand what you're saying is without having to understand prior to doing this analysis if features are correlated. I'm not aware right now of any class of algorithms that can tackle multicollinearity right off the bat, but I would be interested to investigate that.
Cool. I mean, for example, if you knew that things were correlated,
yes,
could you then use that when you do your perturbation in some way?
Well, I guess you would need to do some filtering of your data. If you pipe it directly to the permutation importance algorithm with both of those or multiple features related to each other, it will end up relying on the correlated features. But I guess this is why it's customizable, is that if you have prior information about features being correlated, you can potentially either filter certain features out when you're doing your feature importance process. But you can also use the dendrogram visualization that I showed you to understand that and prune and maybe cluster together features that are too strongly correlated to calculate feature importance. So that's also very helpful if you know or don't know about feature correlations prior.
Cool, thank you.
Yeah. Thanks.
Any other questions? Cool. Thank you, Milind.
Awesome. Thanks.
All right. So we have our final presentation from Harish. He's been working on integrating VW with ONNX, and he's been working with Jacob.
Thanks, Jack, for that introduction. Hey, guys. Yeah, my name is Harish. I guess I'll just jump right into the presentation then. Yeah, so as Jack mentioned, I was working with Jacob this summer on a project to export VW models into ONNX format so that we can now intercorrelate the two. So just before we get into it, a brief introduction of me. My name is Harish. I'm a senior at Georgia Tech, and I'm doing a BS in CS and math. My mentor was Jacob Albert, and my background interests and some research I've done before is in RL generalization and just theory in general. So just to start off, why do we care about having ONNX work well with VW? There's a few main reasons. The first one being you can now use it with different frameworks. So if we can export a VW model to ONNX, a lot of big frameworks like PyTorch and TensorFlow also export to ONNX. So we can now use the strengths of different frameworks and bake into like a single model. You can think of it. Another one is you can abstract the computation of VW away from the entire VW framework, so that you don't have to rely on importing all of VW whenever you want to run a VW model. And of course, you can now compare results you get from VW to maybe results you get from different models a lot easier. And finally, adoption. ONNX is standard across a lot of different frameworks for the format of models. And if we can export VW models into ONNX, it means that a lot more people can start playing around with VW. So in order to get started with using ONNX in VW, there are a few steps we have to take. And the first step is introducing sparse operators to the ONNX operator set. So a big strength of VW is that it uses sparse operations in order to sparse computations, which is why it's really fast in a lot of cases. The problem is ONNX doesn't have default support for sparse operators. So this is the first thing that we had to introduce. On the right-hand side, you see like the reduction stack of just generic problem that you might run with VW. And the bottom of the stack is GD, which is a known regression problem that we can easily solve. So that was the first step to create this operator set. So basically, this step was introducing a new sparse operator GD predict to an operator set. And using this, we can now perform inference on a lot of different types of VW models, including multi-class cost-sensitive classification, some forms of contextual bandits, and recently you can export a model you trained using label-dependent features into ONNX as well. So after you define the operators that you need, so in this case GD predict, you now have to introduce some efficient implementations to actually run the model when it reaches these operators. So that is done in ONNX runtime. So on the right, you can sort of see the process. So you define the operator in ONNX, and then you define the implementation on ONNX runtime, and then you can run the model wherever you can run ONNX wherever you can use ONNX runtime. The third step, and this was definitely like one of the more complicated steps that also might need a bit more thought, is that you use the VW parser in order to convert examples into a vector format that you can now run through a model. So you can think of this as just sort of intermediate step. So if I take in a VW example and I run it through the parser, that is sort of how I convert between a VW example and something that ONNX can understand. And the fourth step is to introduce a conversion tool for VW models that we can support. So even if you have the operators, you still need to define the model structure that will perform the same computation that VW is doing under the hood. And finally, after you have an exported ONNX model, we should be able to show that we can run this model in ONNX runtime, and which also means that we can run it anywhere the ONNX runtime is being used without having to rely on the entire VW framework being imported. So here is an example of just like a sample model that might be the output of the project. So you can see on the top here, there's two inputs. One is features and valid classes. So this is for a cost-sensitive classification example. So the features are run through multiple instances of our GD predict operators. And this does the same computation that VW does under the hood when it's running a regression inference. And the results of this are concatenated, and you check it against the classes that you want to check against. And you just choose the example with the least costs. So yeah, this is just like a sample of what an ONNX model might look like. VW model might look like in ONNX. So now I'm just going to introduce just a toy problem. So the purpose of this is not to really show like this problem at all. It's really to show that we can use a generic ML problem that we might have, and that we might use VW to solve, but now we can do it in ONNX as well. So yeah, so basically the idea behind this problem is you have a data set of NASA stars, and they have a lot of different features. And I'm trying to classify whether these stars are hazardous or not. Yeah, so that's sort of the like basis behind the problem. So the first step was to just convert this data set into a VW format, which is pretty simple, just generic cost-sensitive classification format. And then you train a VW model on this format. So here you can see like the trained model. Just so up to this point, this is all just native VW, nothing special here. And the bottom half is where this project comes in. So the first thing that you do is you want to create the model. So this is another step that maybe that I'll talk a bit more about in the future directions we might take. But right now, the creation of the model is done in Python, but eventually we would probably want it to be directly done directly in VW. But basically, the output of the script is an ONNX model, and this looks very similar to the model you saw on the previous page, except in this case there are two instances of GDPredict because there are two classes that you might want to check against, hazardous or not. And finally, you can now use just any generic ONNX runtime application. So in this case, I made a pretty simple like demo application. And all this application does, the important thing to remember is that it really doesn't do anything specific to VW except for the parsing of the examples. So you just start an ONNX runtime session, and you instantiate a VW instance to parse your inputs. But everything after this point, it's running it through ONNX runtime. So there's nothing about VW after you parse the examples. And the result after you get it here, so I can now use this executable I get, and I can use it on any sort of VW example that I'm given. Yeah, so there's just a little bit of logging, but basically I start a runtime, ONNX runtime session, I parse the input, and then I just run it through the model. So yeah, that was sort of like a toy example, I guess. And so this was like a pretty simple example, but one of the more exciting like implementations of the example would be an RL client lib. So unfortunately for this presentation, I couldn't have RL client lib completely done. There are some like unit tests that I can get working with it, but the complete implementation will take a little bit more time. But basically what RL client lib does, for those that are unfamiliar, it runs basically, there's a world here, and the world gives you context. It's just a contextual bandits problem, basically. You perform decisions or actions on this context, and that loops around. And here, the RL client lib is an actual model that's being inferenced right now. So traditionally, this would just be maybe like a VW model or whatever framework you're using, but usually a VW model. And you send these logs to a separate instance, which will now train new models synchronous or asynchronously. And you'll output a new model here to be fed back into RL client lib whenever you have enough training data to update the model. So where this project would step in would be, instead of running this in VW, you would run it in ONNX. And once you run it in ONNX or ONNX runtime, there are a lot of like optimizations you can make that maybe weren't available with VW. So, and then of course, when you create the new model, you're just going to export it to ONNX again, and then continue running it in ONNX runtime. So yeah, unfortunately, we couldn't get to that, but it is definitely a to-do. So the final results of the project can be summarized basically as a few main bullet points. The first one is an end-to-end pipeline to export and run VW models in ONNX format. There are a few caveats to this, the main one being that the export is not being done directly in VW, but rather a script. But this is definitely a further like step to take. And the second main result is that we can export different like VW types into ONNX. So we saw like on one of the previous slides, we can do just regular cost-sensitive classification. We can also do contextual bandits. We can also do label-dependent feature mode. And there is at least the beginning for an operator set that we can now propose to ONNX, which supports sparse implementations of regular operators. And when we believe that VW can be a main driver for this sort of push, because sparse operators are definitely gaining in popularity, and it's surprising that ONNX doesn't have native support for it yet. And finally, a proof of concept that these models can now be used in systems that might not regularly support VW, or it might be a lot more effort to use VW in, such as our client lib. As far as next steps, the main next step from a technical side is there is still not support for generating interactions, which is a big part of some VW models. And of course, we want to actually propose this sparse operator set to ONNX, as well as maybe have a holdout set of operators specifically for VW. And finally, just VW native support, meaning you can run and export these models directly in VW without having to rely on any other scripts or anything. So just as a final wrap-up slide, the main things I gained from this experience, which was a whole lot, but I just want to put a few of the bigger ones in a few bullet points. The first one was this was my first meaningful and larger contribution to an open source project. And I guess I didn't really realize like sort of how many moving parts there are in open source projects and how I guess rewarding it is to actually be able to contribute something that multiple people will see, multiple people will be able to work on, and it's really pushing the field forward in a way. The second one, this is my first experience with a large C++ library, and definitely changing some things in that was somewhat of a learning curve. But Jacob especially was very helpful for this, and I really think I learned a lot on this aspect throughout the summer. Third one, this is my first time using ValPowerRabbit as well, and it sort of gave me an appreciation for all the different things ValPowerRabbit can do and all the considerations you have to take into just making these models, efficient or to make them better, I guess, than just running like sklearn.fit. And of course, an introduction to a great mentor and a very interesting project. Yeah, Jacob was definitely an indispensable resource throughout the summer. And I hope to at least be able to work on, some sort of open source part of ValPowerRabbit for the near future, at least to finish the loose ends of this project. So yeah, that was the end of my presentation. Are there any questions?
So with respect to sparse operator support in ONNX, what is the plan for pursuing that? Yeah,
so I guess the idea behind the project was that we can show that this is a valuable thing to do because VW does it efficiently, and ONNX has not done it yet, even though it is a very valuable thing. So we're sort of seeing VW as the driver behind this is something you should really consider using. The good thing is
what is the next step here in terms of getting sparse operator support into ONNX?
I might have a bit more context here, since we haven't really started pushing the reintroduction of operators to ONNX. Kind of the big things is one, remove the VW specific terminology from it and kind of document and explain how this is to be used, show how it might be used for other models as well. But sort of the big kind of open question is, can it be done in an efficient manner in sort of the majority of the ONNX use cases, which is on GPU. And I'm not clear whether that is the case, which is why we have that second choice of potentially shipping a custom VW-specific operator set in the interim to enable VW models to interoperate with ONNX, but it'll basically be under an understanding that you need a runtime that can support the VW operator set, which happens to include exactly one operator. The other bit is that I suspect we'll need to introduce additional operators for interaction generation, just for efficiency. And that's another thing that might be useful more broadly. On the flip side, there's more momentum around sparse operators because a lot of the larger embedding models, attention, things like that, tend to like sparse because they're very large. So I suspect that might be also an in.
Yeah, a lot of people have also been playing around with sort of these projection into a high-dimensional feature space through a sparse hash type approaches.
Mm-hmm.
So I'm thinking back to the lecture that Sanjay Gupta gave, for example, with a fly hash. So that's another
exactly.
Using this kind of you want to use some sort of hash operation, which is it's sort of getting at the same kind of thing as the interactions.
Yeah, that's actually a really good point. We should, when we're ready to propose this, we may want to actually include this as a secondary. Here's another thing that can be enabled with this.
Yeah.
Thanks for reminding me of that.
Okay, I think we're nearing the end. Jack, right? Any other questions for Harish?
I'd just like to quickly say thank you, Harish, and please feel welcome to keep involved.
For sure.
Yeah, I've stated it before, but I just want to underscore this again for Harish and everyone else. We will be thrilled to have more contributions from all of you going forward.
Yeah,
Yeah.
and I just want, I'm sorry, go ahead, Jack.
Oh, I just want to say from my perspective, it's just been so awesome working with all of you. It's just been a great addition to our community. So thank you for all of the hard work you've done.
Yep, same. I was going to echo Jack's thanks to our presenters today, Harish, Milind, and Sharad, but also to Mark and Cassandra and Newton that went yesterday. It's been a fantastic opportunity for us, and hopefully it was a good experience for you all to participate in our RL Open Source Festival this year. John, did you want to add anything?
So I don't have anything to add beyond that much. Thanks a lot, and I look forward to trying to incorporate these into our standard work in the future. It seems like a lot of good progress was made.
Yeah, and you all had fantastic presentations. So, very nice work. Okay, well, with that, then, Jacob, you can go ahead and stop the recording. Thank you all. For our students, good luck in your school year next year. And we hope that you stay interested and whenever you have a chance, contribute. Thanks.
Thank you.
Thanks all.
Thanks, everyone. It was a great summer.
Thanks. Bye-bye.
Thanks.